Record.
So hi everyone, my name is Sarah O'Rourke and today I'm going to be talking about the move to more renewable sources of electricity in Ireland, some of the challenges that this brings and how the control centre tools that we're developing are enabling greater levels of renewable generation on the system in Ireland. So on to the next slide here. Has that gone for the thing? It hasn't gone for me. Cool. So, okay, that's too far. So I'm an engineer at EirGrid, the transmission system operator for Ireland. And if you don't know, EirGrid operates and develops the electricity grid in Ireland. So in a nutshell, we're getting the power from where it's generated to where it's going to be needed. So as the demand for electricity is growing in Ireland with an increasing reliance on electricity in industrial uses and in domestic uses, with the connection of more and more data centers and with the move to more electric vehicles and electrification of heating, the CO2 and greenhouse gas emissions from the electricity sector are going to continue to grow unless some really significant changes are made to the way that power is generated. So in response to this, the Government of Ireland have set some really ambitious renewable generation targets for us for 2030. Originally, that target for 2030 was 70%, but as of late last year, we've actually pushed that further and we're now aiming to have 80% of our electricity coming from renewable generation by 2030. So to put that into context of the current electricity landscape, in 2020, 40% of our electricity came from renewable sources. So we're aiming to double what we achieved in 2020 in just 10 years. And it's only 8 years from now. So this here is just showing a map of the generation profile in Ireland in 2020 versus the planned generation in 2030 on the right-hand side. The 2030 target is going to require much more renewable energy sources and a phasing out of fossil fuels. So Ireland's generation profile is going to have to undergo a massive transformation in the next 10 years with, you can see on the map there, with a huge growth in offshore wind down the east coast of Ireland and a huge growth in solar plant, as well as continued growth in onshore wind. But of course, there's going to be plenty of additional challenges that are going to come with relying more heavily on renewable generation. So the first challenge is we have to keep some power in reserve in case of a generation trip. And conventional units are really readily available for ramping and really readily available with reserve, whereas you can't just turn up the wind to meet a ramp up in demand. So the ramping and reserve difficulties are going to pose a challenge to us. The second challenge is that conventional generators are these really large, heavy rotating machines, and these come with a stored energy, which is called inertia, and that gives them the tendency to remain rotating at the system frequency. So this is particularly important following any disturbance on the power system. If, for example, a large unit trips off and then you're left with a mismatch between generation and load, the system inertia is going to act as a buffer against any rapid change in system frequency. The rate of change of frequency, or the rock-off, is very carefully monitored, as any system event that results in a high rock-off can potentially lead to some instability in the power system. So if we're looking to having greater levels of renewables, wind turbines are much, much lighter resources, and solar plants, they don't have an associated inertia that come with them, I don't think. So renewables don't come with this same stored ability to help absorb any change on the power system. And then the third challenge is keeping the voltage of the system in range. In some areas of the system and of the country, the conventional plants contribute really heavily to voltage control. So this is going to become much more difficult as the level of renewables increase and the conventionals aren't running as much. Wind farms, they do provide some reactive support, but it's not to the same degree as the conventional sets. So managing the voltage is going to become much more difficult without some intervention. So these challenges, they translate into operating the system at limits that are far beyond the system conditions that we're currently very comfortable operating at. This slide displays the results of the studies carried out to determine some of the operational parameters that will be required to meet the renewable targets. So the red star in each graph displays the current operational limit for all of these parameters. But just to note here, before we carry on, that these studies were carried out when the RESI target was 70% for 2030. And now that we're aiming for 80%, we're going to have to push the system even further. So without going massively into the detail of these studies here, You can see that for each parameter. So we've got inertia on the top, which we talked about, the maximum rock off, the SNSP, which is sort of a proxy for how much of the demand is being met by renewable generation, and the number of minimum units on the system. You can see for each of these parameters, to meet the 70% RESI, or now 80%, we're going to have to operate far beyond the current operational limit. So you can see the bulk of the graph is far beyond the red star, marked at the gold star, where we're going to need to operate at. So, we're very comfortable at the moment at the red star, but in order to relax the limits without compromising the operational security of the system, 3 new decision-making tools were identified as necessary for us to use in the control center, where we manage the electricity system. So these are the 3 tools that I'm going to talk about now today. Come on in there. So the first one is the ramping margin tool, or RMT. So renewable generation relies really heavily on very accurate forecasting, but as the level of renewables increase, so does the magnitude of the error in that forecasting. And then we're also dealing with uncertainty in the interconnector flows and errors in the load forecast. So RMT is going to help the grid controllers to identify some periods where uncertainty in these forecasts might jeopardize the secure and the reliable operation of the power system. The bar graph in the top right, labeled with ramping margin and generation increase, is just a quick illustration of what ramping margin is. So on a unit level, the available ramping margin is the difference between a unit's total capacity to ramp upwards and its scheduled generation increase. So say you're looking forward a time frame, say you're looking forward 3 hours. It's what's left over between the unit's max output and the scheduled generation of that unit in 3 hours. All units have this available ramping margin, and then we can sum up all these unit level ramping margins to give a system-wide ramping margin. And this is shown in the graph on the bottom, where the red line is the total available system ramping margin. RMT then is going to monitor the available ramping margin and compare it against the ramping requirement that's needed to operate the system securely, while accounting for any of those errors or uncertainty in the forecasting. And this requirement is shown there by the orange line in the graph. So where our ramping margin is above the requirement, we're in the clear and we wouldn't expect any problems with ramping. And during these periods, the grid controllers can safely schedule the maximum amount of renewable generation and be confident in running maybe 1 less conventional generator than they normally would, so less than our minimum number of units that we're running at the moment. However, when the ramping margin dips below the requirements, there may be a risk to the system. So RMT is going to give the grid controllers some advance notice of these periods and allow them to schedule more defensively or more conservatively in order to meet the demand. So we're going to maximize wind and solar where possible, and then the large conventional plant would only need to be scheduled where necessary. The second tool, LSAT, is our look ahead stability assessment tool. So LSAT looks forward 8 hours from real time, and it uses a future network and a generation profile that's based on a load forecast, on HVDC interconnector schedules, on unit schedules, and on outages that are coming up. And it runs a collection of almost 800 dynamic contingencies. These contingencies are the systematic tripping of generators, tripping of key transmission equipment and circuits, and of the HVDC interconnectors. It can simulate fault on the line. It can simulate system separation between the north and south systems, and just a huge range of other system disturbances. So for each of these contingencies then, it's going to run a load flow to check, does the system frequency stay within the defined secure ranges for frequency? And it checks for any extremely rapid changes in frequency that would be outside the rock-off limit. Essentially, what it's doing is it's checking, will the system stay secure if something's going to trip? And if it's not going to be secure, it's going to flag it up to the grid controllers as something to preemptively take an action for. We can use this then to say, okay, if there's an event in a couple of hours, like a lightning strike in the Midlands, how would the generation around Ireland, in Cork, in Donegal, and in Dublin respond? LSAT will let us look forward over the scheduled horizon and see where the frequency might be particularly vulnerable to a disturbance, possibly because there's more wind scheduled and less of the conventional generation that helps keep the frequency steady with the inertia. The graph on the bottom left is an example of the analysis that the tool does. So you can see from this graph that leading up to the generator trip, the system frequency will be quite steady. LSAT then can simulate the generator tripping, and it will show that the system frequency is going to dip right down before recovering and climbing back up in a few minutes. And it's the assessment it's doing here is at the nadir of the frequency, is the frequency within limits, and is the rate of change of frequency when it's dropping down or recovering back up going to jeopardize the secure operation of the system. If it's not going to be secure, the controllers are going to take an action to resolve the issue. So then finally, we have our third tool, the voltage trajectory tool. And the idea with this one is there are acceptable voltage ranges for the transmission network. And there tends to be voltage issues where the voltage will drift out of these ranges at some times like peak demand in the evening when everyone gets home from work and turns on the kettle and start making dinner at 6 o'clock. Or during the night when the demand is at its lowest, or in any scenarios with really high penetration of wind generation. Like LSAT, VTT is going to look forward a number of hours into the future, and it'll optimize all the voltage controls and voltage set points on the system so that all the reactive power resources can be managed more efficiently to maintain a healthy voltage profile. VTT is going to provide guidance and some advance notice to grid controllers on any potential static voltage issues that will be arising over the time horizon. And it will suggest the corrective actions that grid controllers can take to solve any predicted voltage issues in a way that will minimize the actions that they're taking from 1 hour to the next. So something that they do now will help solve an issue that might crop up in 8 hours time. So they're managing it more efficiently than they would be without it. It's something that they're doing like intuitively now, like they are well able to control the voltages on the system, but as the wind generation continues to increase, it's going to become more and more difficult to manage in an optimized way. So that's where VTT is going to step in. The image on the screen here is the network overview for the Irish transmission system, where each node on the map represents a substation. And one of the features of VTT is that it can create a heat map that color codes all the substations according to voltage, where red is going to be high voltage and blue is low voltage. And it can simulate how this is going to change over the study horizon. So this is just a snapshot of half an hour, but over say 8 or 10 hours, it can show you how your voltage is going to change, which is really interesting because at certain points in the day, you're more likely to have high voltage anyway. But it'll just highlight maybe if something's going a little bit outside what you'd expect. The red and orange cluster on the right-hand side is the Dublin area. And Dublin is typically a very tricky area to manage as the load is very high relative to the rest of the country, obviously being the load center of the capital. So VTT is going to just help assist the grid controllers in keeping the voltage there and all around the system within limits. So in summary, we have our 3 tools that are working to assist the grid controllers in making decisions in the control centers. We have RMT, which is looking out for uncertainty in the renewable forecast, and it's ensuring that we have enough ramping margin and reserve. We have LSAT, which systematically trips generators and transmission equipment to see, will the frequency remain secure, even without conventional generators to act as a shock absorber in any frequency event. And then we have VTT, which optimizes the voltage controls and set points on the system to ensure that the voltage is going to stay in secure ranges, even with very high levels of wind. These 3 tools are enabling the island of Ireland to reach just record-setting levels of renewable generation. In February early this year, the wind generation hit a record high of 4,584 megawatts, which made up 86% of the demand at the time. And then later on that night at midnight, wind energy reached a peak of supplying 96% of the all-island demand. So hopefully with these tools, with the help of these tools, we can achieve these record-setting levels of wind all year round so that we can reach the 80% target on average. So that's all from me. Thank you very much for listening, and I'd love to take any questions.